Vacuum decay is one of the strangest ideas in modern physics. It is not about something exploding in some distant part of the universe. It is the possibility that empty space itself may not be permanent. That sounds like science fiction, but physicists have solid reasons to study it. In this video, we will explain what physicists mean by a vacuum, how the Higgs field turned this from a vague idea into something they can calculate, and what it would mean if space shifted into a different state and raced outward at nearly the speed of light. The goal is clarity, not panic. Beneath the dramatic headline sits a quiet, profound question. Is the background state of reality truly stable, or only stable for now? To understand any of this, we need to settle one word right away: vacuum. In everyday language, a vacuum sounds like simple emptiness. In physics, it means something more precise. It is the lowest energy state available to a field. Fields are not exotic extras layered on top of reality. In modern physics, they are the underlying ingredients, and particles appear as excitations in those fields. So when physicists talk about the vacuum, they do not mean a perfect philosophical nothing. They mean the calmest state those fields can settle into. Empty space, in that sense, is not empty in the ordinary way. Still has structure. It still has properties. Can even, in principle, have more than one possible energy level. Once you see that, the subject becomes less mystical and more physical. The question becomes whether the state of space itself is the lowest one available. Once you treat the vacuum as a state, a strange possibility appears. The state we live in might be stable, but not perfectly stable. A simple picture helps. Picture a ball resting in a valley. If that valley is the deepest place in the whole landscape, the ball has reached its final resting place. If a deeper valley lies beyond a ridge, the ball can sit where it is for a very long time without being in the true lowest state. That is the basic idea of a false vacuum, also called a metastable vacuum. It does not collapse at once. It does not look dramatic. It is simply not guaranteed to be the absolute bottom of the landscape. And that matters because metastable does not mean delicate in the everyday sense. A metastable state can last for absurdly long stretches of time. Longer than stars. Longer than galaxies in anything like their current form. The unsettling part is that something can look perfectly calm and still not be final. For a long time, that picture sounded almost philosophical. Then physicists found the Higgs boson and the discussion changed. The Higgs field is not just another ingredient in physics. It is woven into the vacuum we live in. Once physicists measured the Higgs mass at about 125 giga-electronvolts, they had a crucial input for real calculations. Add the mass of the top quark along with a few other measured quantities, and the question becomes much sharper. Physicists can ask whether the mathematical shape associated with the Higgs field points to a vacuum that is fully stable, or one that is only metastable over immense spans of time. That is the pivot in this story. A discovery inside a particle collider gave physicists a way to say something meaningful about the long-term stability of the entire universe. Those particle masses matter because the landscape is not fixed once and for all. Quantum effects can reshape it. In plain language, the Higgs field has an energy profile, something like terrain with slopes and valleys, and that profile changes when physicists include the influence of other particles. The top quark matters especially because it interacts so strongly with the Higgs field. Those interactions can tilt the landscape at higher and higher energies. If the numbers fall one way, the valley we live in stays the deepest one. If they fall another way, a deeper valley can appear far off in the distance, and our present vacuum becomes metastable instead of absolutely stable. That is why precision matters so much. Tiny shifts in measured particle properties can move the verdict from stable to borderline to metastable. And with the standard model alone, using the measurements we have, the picture often lands uncomfortably close to that boundary. Where does the evidence leave us? If you take the standard model and extend its equations to very high energies, many calculations place our vacuum in an uneasy middle ground. It sits close to the line between fully stable and metastable. That distinction matters. Metastable means stable for a very long time, without any guarantee that it remains the final state forever. The clearest picture is still the simplest one. A ball resting in a shallow valley. It is not rolling anywhere today. It may never roll on any timescale that matters to us. But if a deeper valley lies beyond a hidden ridge, then this is not the lowest resting place available. Physicists did not reach that picture by chasing cosmic drama. They reached it through precision measurement. The Higgs boson mass, the top quark mass, the strength of the strong force. Put those numbers into quantum field theory, and the Higgs landscape can bend in a way that suggests our vacuum may not be the deepest one possible. We still have to be careful. No one has observed that verdict directly. It depends on how physicists extract some quantities, especially the top quark mass. It depends on technical choices in the calculation. And it depends on one major assumption: that no new physics appears at higher energies and changes the landscape first. So the careful answer is narrow but important. Under the Standard Model alone, many analyses favor metastability, but the result sits close to a boundary, and that boundary is sensitive. That is why physicists take the idea seriously without treating it as settled fact. If that picture is right, the next question is hard to visualize. How does space change state at all? Physicists describe it with bubble nucleation. The word bubble helps if we use it carefully. This is not a bubble of gas, and it is not a fireball. It is a tiny region where the field has slipped into a lower energy state, a new phase of the vacuum forming inside the old one. Quantum tunneling provides the route. In ordinary life, a ball trapped behind a hill has to go over the hill. In quantum physics, a system can have a small probability of appearing on the other side without crossing the barrier in the classical way. That does not mean anything can happen with ease. It means the path is not completely forbidden. So in the false vacuum picture, somewhere in space, through an unimaginably rare quantum event, a tiny seed of true vacuum could appear. At first it would be microscopic, almost nothing to see. No countdown, no crack racing across the sky. Just a minute patch of reality that no longer matches the vacuum around it. That is the moment vacuum decay becomes concrete. It is a phase change in space itself. A new version of empty space beginning locally inside the old one. This is the part people remember because it is severe and simple. If a true vacuum bubble forms and it is large enough to be energetically favored, it does not stay put. The lower energy state expands. The boundary between the two vacuums moves outward at nearly the speed of light. That speed matters for a deep reason. In our universe, no usable warning can outrun light. So if the bubble wall is already moving at that limit, no signal can race ahead of it and give distant observers time to prepare. The first meaningful sign would be the event itself. From far away, there would be almost no cinematic buildup. No slowly brightening beacon. No alarm sweeping across the sky years in advance. Ahead of the wall, physics is still normal. Behind it, the vacuum has changed. The boundary between those two states is the catastrophe. So when people say the universe could delete itself at light speed, this is the idea underneath the phrase. It does not mean all of space detonates at once, and nothing in the evidence says this is about to happen. It means that if vacuum decay ever began, the new vacuum would spread so fast that anything in its path would get no meaningful warning before the altered laws of physics arrived. This brings us to the most important correction in the story. Vacuum decay is not mainly about smashing things. It changes the conditions that let things exist in the first place. If the vacuum changed, the Higgs field could settle into a different value. Because the Higgs field helps set the masses of fundamental particles, that shift would not stay in one corner of theory. It would run through the structure of matter itself. Particle masses could change. Interaction strengths could change. The balance that lets atoms, chemistry, solids, stars, and living tissue hold together might no longer exist in the same form. A useful analogy is a piece of music that changes key in the middle, though the real change would be far more extreme. The instruments are still there in some sense, but the relationships that made the music coherent have changed underneath them. So inside a true vacuum bubble, matter as we know it would not be burned away by ordinary heat or blown apart by a familiar shock wave. It would fail because the rules that made familiar structures possible had changed. That is why the idea feels so absolute. It is a rewrite of the baseline settings of reality. At this point, the responsible question is the simplest one. Should we be worried? Based on current standard model calculations, no, not in any practical sense. Even in the metastable scenarios that many central value analyses favor, the predicted lifetime of our vacuum is vastly longer than the current age of the universe. Longer by such an enormous margin that ordinary fear does not fit the science. That is why physicists can discuss vacuum decay seriously and stay calm. The interest is not that doom is waiting around the corner. The interest is that our best existing theory, pushed to extreme energies, seems to place reality near a remarkable boundary. So this is not an everyday danger. It is a frontier question. The significance lies in the uncertainty itself, where it comes from, what assumptions create it, and what it may reveal about the limits of the standard model. This is where the story leaves a simple yes or no answer behind. When physicists say our vacuum may be metastable, they are not reading that directly from the sky. They start with precise measurements we can make here and now, combine them with equations we trust, then extend those equations to energies far beyond anything our labs can reach. That step is where the uncertainty enters. We have measured the Higgs mass. We have measured the top quark mass. We have measured the strength of the strong force. The final stability verdict depends on the exact values, especially the top quark, because it couples strongly to the Higgs field and helps shape the Higgs landscape at higher energies. A tiny shift in the inputs can change the result. A small change in the top mass can move the answer closer to full stability or deeper into metastability. Different calculation methods matter too, because physicists are working at the edge of what the standard model can tell us with confidence. Then there is the biggest unknown. We do not know whether the standard model is the final theory. If new particles exist, if some additional field couples to the Higgs, or if gravity changes the picture near the Planck scale, the whole landscape could change. The deeper valley might disappear. A new barrier might appear. Or the vacuum could prove less stable than we think. Physics has not shown that the universe is doomed. It has shown something narrower and more interesting. With the theory we have now, and the measurements we trust now, empty space appears to sit close to the line between truly stable and only extraordinarily long-lived. That is why this question remains open. It sits at the boundary between precision measurement and the limits of our current theory. Before we end, it helps to separate the dramatic picture from the practical reality. Vacuum decay is a serious idea in theoretical physics. Based on current standard model estimates, it is not a meaningful near-term danger. Even in the metastable picture, the expected lifetime of our present vacuum is vastly longer than the age of the universe. Longer than human history. Longer than the lives of stars. Longer by absurd margins. This is not a reason for alarm. It is a reason for perspective. The importance of the idea is not that space is likely to fail tomorrow. Modern physics can ask this question at all, and the answer seems to depend on a delicate boundary in the laws we know. That brings us to the deeper point. The vacuum decay hypothesis matters because it shows where our confidence ends, where our measurements become decisive, and where the standard model may no longer be the whole story. If you want more videos like this, you can like the video and subscribe to the channel.